All right, so we're gonna go through 8.1 today, and right. So let's pick it up from the beginning here. Okay, so okay, so a vector is a quantity that has both magnitude and direction. Usually, you hear this phrase in science, right? Like yes, no. Okay, so okay, so if I were to tell you, there are, I don't know, 5 liters of water here, that's just quantity, right? If I tell you, oh, look, he's running at, 6 meters per second, that's just quantity. But if I tell you, oh, look, they're running at like 6 meters per second north, now I've given you two pieces of information. There's a quantity and there's a direction. There's a magnitude and there's a direction. So a vector is a quantity that has both magnitude and direction, right? So velocity is one that I just mentioned. Force is another one, right? There are 5 newtons of force, let's say, acting, on this, upward, right? That is vector quantity, okay? So a quantity which has only a magnitude and no direction is called a scalar. So remember when we were multiplying, matrices, and I said, if you want to multiply the whole matrix by 3, that number 3 is a scalar, right? So in the world of vectors, that's just a number that doesn't have a direction. All right. So we say the velocity of an object is 6 meters per second east, but the speed is simply 6 meters per second. So here, yeah, they're both talking about how fast something is going, but speed is a scalar quantity. Velocity is a vector quantity because it also has a direction. Okay, so let's take a look at this. A ball thrown northwest at 60 meters per second. Is this a vector or a scalar? Vector. How about a tennis ball served at 110 miles an hour? Scalar. And the last one? It's a vector. Okay. Because a vector has a magnitude and a specific direction. Now remember, a direction can be, like if you look at like the 360-degree world around us, the direction, really could be, in any direction, right? It doesn't have to be like horizontal or vertical. So the best is to represent vectors as an arrow diagram, or it's also called a directed line segment. They pretty much look like rays because they have a point where they start and a point towards which they go. So look at the vector here. The vector starts at an initial point and then it ends at a terminal point. Those are the words I choose to use because they're more descriptive and they're easier to, keep, like, to remember. You can also say the tail or the tip, but again, those are not as descriptive, so it's easy to get confused, like which one is the tail, which one is the tip. But if you say initial point and terminal point, then we know. Okay, so A is the initial point, B is the terminal point. Okay, now what is the symbol for a vector? Remember when we were learning about rays and segments and lines? They each had their own notation. Okay, so there are a couple of ways you can represent a vector. One is 2 capital letters because the initial point and the terminal point both get capital letters. So it's 2 capital letters, initial, then terminal. So A, then B. You can't mess up that order. Initial, then terminal. And then it's not an arrow, it's a half arrow on top. Okay? Not a full arrow. That means vector. You can also give the vector a special name that usually gets a lowercase letter. Like if you wanted to call this A, then it would just be vector A. And then in print, the shorthand notation is just bold-faced lowercase letter. That's just an A. Obviously, that is just in print, and then these you can use interchangeably in like writing. All right? Okay. So let's talk about the standard position of a vector. When a vector is in standard position, just like angles in trig, The initial point is at the origin. And then from that, it's literally just like an angle. So actually, like some trig is going to creep in here because, that's how we can identify a direction. So if it's completely lying along the x-axis and it's horizontal, then the direction of the vector is, 0 degrees, or, it's pointing, like to the east or something, right? But this is 0 degrees. And then how do you specify a direction? It's literally the angle by which it's rotated. So right now, this has a direction of 35 degrees. And if we all agree where the starting point is, it's at 0 degrees here, then 35 degrees is a very precise way of stating the direction. Okay? All right. So the direction then is the angle between the vector and a horizontal line. The magnitude is physically and literally the length of the segment. And we use those bars. It's not absolute value. It's magnitude of A, right? So this would be the magnitude, the size of the vector. Now, vectors are usually scaled down, right? So for example, if I wanted to represent a vector of like 300 meters per second, I'm not going to draw anything that's 300 anything units long, right? So I scale it down. And literally the way in which you measure these is like you take a physical ruler, right? And you would measure this segment. Now, if you measure that segment on your paper with a ruler, it should be 2.6 centimeters. Okay. And the scale for this one is 1 centimeter is 5 feet per second. So the magnitude of this is 5 times 2.6, 13 feet per second, right? So if I were to say what this vector is, I would say this is, the velocity vector, 13 feet per second, going at an angle of 35 degrees. Any questions on what we're talking about here? Okay. Yeah.
So the magnitude can be written as just 2.6 centimeters?
No, because 2.6 centimeters is the length of that specific arrow. But if it represents the velocity of something, then we've scaled it down, right? So just like if you look at a map, if you measure like the distance between the US and UK, right, it's not like 10, right? If it's 10 centimeters. Okay. Yeah. Okay. So, all right. So how do you find the direction of a vector? All right. To find the direction of a vector A, this should have had a little arrow on top. Okay. So what we do is, this is the vector, right? In blue. You would take a ruler and you would draw a horizontal line at the tail or at the initial point of A, right? So just draw a horizontal line. Now you measure the angle from the horizontal line to A in the counterclockwise direction. So yes, it would be like with a protractor. The point of this chapter in this class is not for you to take out your protractors and measure this, but we're going to do other things later, but you should know where these measurements are coming from. So this is let's say this is 115 degrees. That's what the direction is. So when, somebody taps you on the shoulder and says, hey, what is the direction of this? You don't look for like north, south, east, west. No, it's like, okay, 115 degrees. Okay. So for example, suppose you had a vector that looks like this. Okay. So suppose this is vector B, and we wanted to measure the direction of this. You take a ruler, you draw a horizontal line at the beginning of it. Okay, this signifies 0 degrees. Then the angle from 0 to this would be the angle of this vector. So in this case, let's say it would be like 200 degrees. All right. Okay. All right, so let's talk a little bit more about this. First lesson is a lot of like just vocabulary and getting our, bearings. Okay, parallel vectors are vectors that have the same or opposite direction, but not necessarily the same magnitude. So let's talk about some parallel vectors here. So for example, vector A, right? Vector A is parallel to vector B and C. So I say parallel to vector B and to vector C, and what else? E and F, right? Okay, yes, E is going in the opposite direction, but they're parallel to each other. Equivalent vectors are identical vectors. They have the same magnitude and the exact same direction. So for example, here, vector A is exactly the same as which other vector? C. So we say vector A equals vector C. When you say two vectors are equal to each other, they have the same magnitude, same direction. All right. If you have opposite vectors, that's the same magnitude but opposite direction. So like vector E is the opposite of vector A. And how do you say opposite mathematically? It's the negative, because remember, negative sign represents direction. Sure. Yeah. Okay. All right. So we all know how to add two real numbers, right? 3 plus 7, you guys know exactly how to navigate that. Last chapter, we learned how to add two matrices to each other, right? And that had its own process, right? And we got the sum. Okay, today we're going to talk about this concept of adding two vectors to each other. When you do that, right, the sum, we don't call it a sum, we call it a resultant vector. That's when two or more vectors are added, right? That's the resultant. Okay, so how do you find the resultant vector? There are two methods. I'm only going to focus on the triangle method because we're not going to go too heavily into it. Okay, this is called the triangle method. The other one, FYI, is called, can you close the computer? The other one, FYI, is called the parallelogram method. Okay, so we basically, I have vector A, I have vector B. I want to find A plus B. Okay, so here's what you do. You take A, right? And then you literally take B, you translate it, you shift it so that its initial point is at the terminal point of this, right? So translate B so that its initial point touches the terminal point of A, all right? So we just literally like brought them together. Now you go from the initial point of the first one to the terminal point of the last one. You draw that arrow. That arrow there is your A plus B sum or resultant arrow. Okay? So when I say to add two vectors, I get a third vector, and that's what the third vector is. Any questions? Okay, so now the magnitude of this new vector R, resultant vector, is the size of the vector. The direction is just like we talked about, the direction from the angle 0. Okay, so let's practice one. I'm not gonna make you guys like do these like NASA precisely. So I just want us though to get used to like how we do this. Okay, so this is vector 1, V, right? I'm just gonna take vector 1 and I'm just gonna like, just reproduce this vector here. Okay, so that's vector V. Okay, now this vector W, it's like this is a route, like so this starts here and ends there, and then the other one is gonna pick up where this left off and continue. So this, we're just gonna put it and bring it there. Okay, now the sum, the resultant, we don't say sum, the resultant is from the very, very beginning to the very, very end. That. So that vector is v plus w. That's the resultant vector. Okay, now, how would you find the direction to that? What would you do? Huh? You draw a horizontal line. Where do you draw the horizontal line? At the top or at the bottom? At the initial point here. And then this angle is the direction of that vector. Okay? Okay, so it's less than like 90, right? We're just going to leave it there. Okay, so take a look at this one. Now I have a and negative a. What happens if I draw those two? So here I have vector a. Now I'm going to take the second vector, negative a. That's the second vector. I'm going to start it where this one left off and, whoops, continue. Right? It's okay. So I started here and I ended it. Now the resultant, it's going to be from the very beginning, the beginning of the blue vector to the end of the red vector. How much of a distance is that? 0. It's the same thing because what happens if you have a vector and its negative vector, they cancel each other out. The resultant is 0. Okay? So a plus negative a is 0. Okay, now this is given to us in different form. We have a vector that is supposed to represent a force of 25 newtons north and another one 35 newtons south. So why don't we go ahead and do that? So let's draw 25 newtons north. And then we're going to draw 35 newtons south. I'm going to pick up where this left off. And I'm going to go, okay, so 25 newtons, I kind of estimated that's how long it's going to be. Now 35 newtons, it's going to be south a little bit longer, right? This way? Well, I mean, I meant to do it like a little bit to the side so you can see it. Like that. So what's the resultant? It goes from the very beginning to the very end. Which way is it going to go? Up or down? Which way? Down. Right? So the resultant vector R is going to be 10 newtons south. Yeah. Because it has to be from the beginning. Okay, because it has to be from the beginning of the first one, which is here, to the end of the last one, which is there. No, because from the beginning, no, the shortest distance from the beginning to the end. Okay? Okay, any questions? All right, multiplying a vector by a scalar, that's super easy. Multiplying a vector by a scalar just lengthen, like it just multiplies it literally, like it scales it by that number. So for example, I have a vector A here. The vector 3a is the same exact vector in the same direction, just 3 times longer. Okay? So let's take a look at this. Here is vector x, here is vector y. It says it wants a vector diagram of this. So it wants the combination. It wants the resultant of this. So first I have 3 times x. All right, what does 3 do to the vector x? Makes it 3 times longer in the same direction. So I'm just going to estimate that, that's what happened to 3x. Again, I'm not going to make you guys take out your rulers and do this precisely. We have bigger fish to fry. But I want you guys to know, like, conceptually what this is. Now I have 3/4 y. Okay, so that y is going to shrink to 3/4 of its size. But what about the negative? What does the negative do to the vector? It flips this way. So this is going to get 3/4 of its length, but it's got to flip in the opposite direction. So 3/4 of it in the opposite direction looks like this. Okay. So that's -3/4y. So the resultant has to be the shortest distance from the very beginning to the very end, and that is this. So 3x minus 4y is that green vector. Oh, sorry, 3/4 y. Okay? So like on the test, for example, like I would expect you to be able to draw this setup. Okay, I'm not going to take a ruler and like measure. Okay, did you really do it like 3/4? But just this is shorter in the opposite direction. Okay, does that make sense? Okay, the rain stopped. Okay. Okay, vector components. Okay. So vectors which add to create a vector R are the components of R. So in this one, for example, this red and blue combine or add in order to create this green one. Yeah? Okay. So, when working with vectors, the most useful components are the ones that are horizontal. So for example, what do I mean by that? I can come up with like an infinite number of vectors that add to create that one. So for example, this could be one example, right? Two vectors that add to create this one. Another example, could be this one and this one, two vectors that add to create that one. But the best possible one, I would say, is the one, that goes vertical and horizontal. Okay? Those specific vectors that are vertical and horizontal and they create a 90-degree angle, these are called the rectangular components of something. All right? And when I draw them, I call this vector y and I call this vector x. So I say this is the y component and the x component of that vector. Okay, I didn't have to draw it that way. I also could have drawn it over here and over here, but do you see how those two are exactly the same as the other ones? They're just in different locations. So here, how do I draw the vector components of this? I generally start from the initial side, and I want to find a way to go to the terminal side by going horizontally and vertically. Okay? Okay, so let's take a look at this one. While digging in his garden, Will pushes a shovel into the ground with a force of 630 newtons at an angle of 70 degrees with the ground. So imagine he's like standing here and he's just pushing this shovel into the ground, all right? So it says to draw a diagram that shows the resolution of the force that he will exert into its rectangular components. So we want the resolution of the force into its rectangular components. Let's do this. Okay, which way is Will going to be facing? Let's have him face this way. So that's the vector that represents his force 70 degrees. You know what? Sorry, I'm going to switch things on you just so it's easier for you to see. I'm going to do it this way. Okay, do you see how from the horizontal this is about 70 degrees up? Yeah? Don't go like NASA on me, okay? Oh my God, this looks more like 67. I gotta make it 70. All right. Okay, so how do we label this? This is 630 newtons. That's the magnitude, 630, and we gave it that direction. Remember, it's going downwards. Okay, so we want the resolution into its rectangular components. Okay, where is the initial point? Top or bottom? Top. Basically, we want to know how you go from the initial to the terminal point by just going horizontally and vertically. So I'm going to go down a little bit. That will be my y component. And then I'm going to go to the left a little bit. That will be my x component. These are 90 degrees here. If you want full credit, this is what I want to see. I want to see that this is labeled 630 newtons. I want to see the arrows in the correct locations and labeled x and y vector. All right. If you don't have the arrows, If all you have is this, good for you, you know how to draw a right triangle. Yay. Okay? There is no vector anywhere here. If you have this, still none. If you have this, still wrong, because the arrows are all in the wrong direction. Okay? All right. Yeah, question. Did you have a question? Yeah. Yeah. You could have. If you wanted, you could have done that. But I'll show you that. But sorry, I forgot one other piece of information, that this is 70 degrees. You should show that as well. Okay, but you could have also gone this way. It would have been the same. This way and this way. Right? It would have been the same. This would have been X. X is horizontal, Y is vertical. Do you see how in both of these the X is pointing that way and the Y is pointing down, and right? Okay. The thing about this is sometimes students get confused like where to put the 70. So that's why I do it the other way. Yeah. Okay. So find the magnitudes now of the horizontal and the vertical components of the force. So I know that this is 630. I want to know how big that is, and I want to know how big that is. But oh my God, we know all about trigonometry and right triangles, so we can do that. Yay! Okay, so cosine of 70 is equal to what? X, over 630. Now look, in this equation, this is the magnitude, so I have to put the bars around it. Okay. So then X is equal to 630 cosine of 70. You put it into your calculator okay. Now you gotta be in degrees. Okay? So make sure you are in degrees. It's gonna be 215.5 newtons. Yep. Okay, let's do the Y component. So sine of 70 is equal to Y, magnitude of Y over 630. So magnitude of Y is 630 sine of 70 in degrees. So magnitude of Y is 592.0 newtons. Okay. Now, take a look at this for a minute. We said that this purple vector, the 630, that is the resultant of when you add vector x plus vector y. Now, look at the magnitude of x and y. When I add those two values, do I get 630? No, because vector addition doesn't work that way. It's not just, straight adding of numbers, right? That's why we call it a resultant and not a sum. All right? Okay, so let's do another one. Correct. Exactly. Right? Correct.
The lines, they're not absolute values, right?
They're they're vertical bars. It's magnitude. Just like in the determinants, it was, yeah. Okay, a player kicks a soccer ball so that it leaves the ground with an S, with a velocity of 44 feet per second at an angle of 33 degrees with the ground. Draw a diagram that shows the resolution of this force into its rectangular components. What we have here is a picture that is not a mathematical diagram. So we have to draw a mathematical diagram. All right, we can do that though. So first, I draw the velocity vector. And, I'm going to label it V this time. It's 44 feet per second. All right, so here is the X component. I start from the beginning and I go horizontally this way. And the Y component up. Okay. And what else am I missing? 90 degrees here and 33 degrees there. All right, now I got full credit. Okay, so next, find the magnitude of the horizontal and vertical components of the velocity. So same situation, right? The x component is going to be 44 cosine of 33. That's going to be 36.9 feet per second. The y component is going to be the magnitude 44 sine 33. That's going to be 23.96 feet per second. So now we're going to talk about some very, very important things. Whenever you have any vector, whether it's pointing, whatever direction it's pointing, whether you are working in the southern hemisphere or the northern hemisphere, it's always going to work out this way. It's always cosine, right, is equal to the x component over this. So your x component is always going to be, like in this case, it was the force, the magnitude, times the cosine. The y component is always going to be that original magnitude times the sine. This is why even back in chapter 4, when we were doing the unit circle, I always stressed horizontal x cosine. Remember? Vertical sine y. This is why I do that, right? Because no matter where and which direction you turn, the x, the horizontal, is always the cosine. The y, the vertical, is always the sine. All right? So whenever we have the rectangular components and we have to find the magnitude of the x and y component, you literally just say the full magnitude times cosine of the angle, the full magnitude times the sine of the angle. And so I have that summary here. If you have a vector v, the x component is always v cosine theta. The y component is always v sine theta. Okay? All right? Okay. All right. Let's get to homework. Yeah. Sure.